Hi all, welcome to the last lecture of Pause. Today we will put lots of the things we discussed in previous lectures together to prove a very beautiful theorem. So we will be discussing the reductions of CMC curves. So recall that if I have an elliptic curve E defined over a number field, over Q for example, then the endomorphism ring and the Q bar of E is either Z or E has complex multiplication, namely is either order in an imaginary quadratic field, right? And we also briefly mentioned that if I have an elliptic curve E defined over a finite field of Q, then the endomorphism of E over FQ bar is either order in an imaginary quadratic field. So this is a rank 2 Freeze module, or is an order in a quaternion algebra, which is a rank 4 Freeze module. So today we will discuss, first of all, we will actually give more details on the second case, namely discuss the endomorphism ring of an elliptic curve defined over a finite field. And then we will discuss the relationship between the CM elliptic curve with how often its reduction has this larger endomorphism ring. Okay. So we're going to start with discussing endomorphism ring for elliptic curve over finite fields. Endomorphism rings of elliptic curves over finite field. Okay, so let's first define elliptic curve E over a finite field. Again, we are going to assume that the characteristic of FQ equals to P, which is not 2 or 3. Then we'll have a Weierstrass equation very concretely given by y squared equals to x cubed plus ax plus b, where ab are elements in FQ. Okay. So then we know that, so recall that absolute Galois group of FP bar over FP, let's see, over FP. The absolute Galois group of a finite field is isomorphic as a group to Z hat. So it is topologically generated by a single element, which is often referred to as Frobenius. So from P, let me be more clear. So what that means is that for any element, let's say A in FP bar, very concretely, the Frobenius acts on A by raising A to the pth power. Okay. So then from Fermat's little theorem, we can say that this Frobenius action actually fixes element in FP, right? So this is a generator of the absolute Galois group. So then, so this means that for if I have a elliptic curve E, then I can actually define elliptic curve as a Frobenius action would give me another elliptic curve, which is given by very concretely again y squared equals to x cubed plus a to the p x plus b to the p, right? And then there is the map. The interesting thing here is the map E to E from P. This is the Galois action. One sec. So this is the Galois action mapping every geometric point xy to from P of x, or actually like very concretely, I'll just write it. The action is raised by x to the p, y to the p, right? So this Galois action, as you can see, is different from a Galois action over number fields, over Q, right? As I emphasized, most of the Galois actions is not algebraic map. But you see here that this is algebraic. Right? It's very cool. It's actually algebraic. So this is actually an isogeny. It's very different from the characteristic zero case. So this means that if I consider E defined over the prime field Fp, then this Frobenius is actually in the endomorphism, is the endomorphism of E. Okay. And this, the Frobenius, this isogeny is of degree P and is purely inseparable. Okay. So it has degree P. So this shows you that there exists an element in the endomorphism. There exists an element in the endomorphism ring of E, let's just say FP bar, with norm P, showing that this is exactly why if you have a elliptic curve defined over finite field, the endomorphism ring is always bigger because you have a Frobenius in there. Okay. Now let's discuss, okay, with norm P. So this another thing this implies is that, so first of all, this implies that the endomorphism is strictly greater than Z, right? And then secondly, if the endomorphism ring over FP bar E is isomorphic to O in Q adjoint square root of minus D, if it's an order in an imaginary quadratic field, then it has to be the case that P has to split in this quadratic extension, because otherwise I will not have an element of norm P, right? So this tells you that if the endomorphism of E is isomorphic to an order of an imaginary quadratic field, then P has to split in this imaginary quadratic field. And if this happens, if the endomorphism ring of the elliptic curve over finite field is of rank 2 over Z, then this elliptic curve, we say that E is ordinary. Okay, we will say that E is ordinary. And then now let's discuss if the endomorphism is even bigger to an order O in a quaternion algebra. So first of all, if this happens, we will call E supersingular. There are many different ways to characterize a elliptic curve being supersingular. One way is to look at the endomorphism ring. If just like for elliptic curve defined over a field of character 0, you either have Z or CM case, right? So for elliptic curve defined over finite field, you either have ordinary, which has a relatively small endomorphism ring, or it is supersingular, which has a bigger endomorphism ring. Okay, we will discuss what this case looks like. So even though we have been talking about order in a quaternion algebra, we have not actually discussed very much of what is a quaternion algebra and what does the order in a quaternion algebra look like. So let's discuss that now. Okay. So let's actually define a quaternion algebra. So we'll define a quaternion in a special case. We'll define what's called a definite quaternion algebra. A definite quaternion algebra over the field Q is a Q algebra. So quaternion algebra, we'll call the quaternion algebra B. Okay, over Q is a Q algebra such that B is given by Q plus Q join element alpha plus element beta. So it is a 4-dimensional Q vector space plus Q alpha beta with with multiplication defined by, so first of all, alpha square and beta square are both in Q. Are both in Q, and moreover, both alpha square and beta square are less than 0. So this is the definite part. This is why it's a definite quaternion algebra. And moreover, it is non-abelian. So beta alpha equals to minus alpha beta. Okay, so the elements alpha and beta don't commute with each other. So this defines a division. So quaternion algebra. Note that this definite quaternion algebra is a division algebra. Okay. Note that alpha square and beta square are less than 0, shows you that alpha and beta are not in Q. Okay. So it is a division algebra. Okay, and moreover, for any prime P, then if we tensor B with QP, so we will get a QP algebra. And this QP algebra has two possibilities. So possibility one is that B tensor QP is either still a division algebra, or B tensor QP is isomorphic to the matrix algebra M2 of QP. In the first case, we will say that the prime P ramifies for B, the finite prime P. And then in the second case, we will say that P splits, or sometimes it's called unramified. For B. So every quaternion algebra B is ramified at finitely many primes. And this set of primes actually determines this quaternion algebra up to isomorphism. This set of primes determines B. Okay. And for more information on quaternion algebra, again, I want to recommend a book, which is literally titled Quaternion Algebra. By John Voigt. Okay, great. So we have defined what a quaternion algebra is, and moreover, what we discussed, what happens if I have a quaternion algebra over Q, what happens when I tensor with a completion QP. Okay, there are two cases happens. Okay, next, let's just write down the formal definition of what we mean by an order. It's the same way as how we define the order of an imaginary quadratic field. So first of all, we're going to call a lattice. So a lattice in B is a finitely generated Z-module. A lattice in B is a finitely generated Z-module such that, so I will call this lattice R, such that R tensor with Q is B. Okay, this is a lattice, and then an order O in B is a lattice, which is also a subring. Okay, so this is the same way as how we define an order for an imaginary quadratic field, right? So it's very similar. Okay, great. And then we will see that order is maximal if so O is maximal if it is not contained in another order. And in another order. Okay. So if let E be an elliptic curve defined over a finite field, then the endomorphism ring E over FP bar of E is okay if this endomorphism ring is of rank 4 over Z, then it is isomorphic to a maximal order or order of a definite quaternion Q algebra ramified at only one finite prime, namely P. Okay, so P will be the only finite prime that this quaternion algebra is ramified at. Okay. Okay. Okay, great. So as we already discussed, this is the case when we say that E is supersingular. And note that from the definition of ordinary and supersingular, they are all about the endomorphism ring over FP bar. Okay, so this means that this property of being ordinary or supersingular does not change. So this is a geometric property. So it does not change over base field extension. So supersingular or ordinary is geometric property. And which means that it is determined by the isomorphism class of these curves over a P bar. So determined by the J invariance. Okay, it's determined by J invariance. Okay, great. Well, so let's talk a little bit more about what this definite quaternion algebra B looks like if I have a supersingular elliptic curve E. Okay, so this requires us to talk about this quaternion algebra B, which is ramified at P. Okay, so when P is ramified for B, then as we already discussed that the algebra B tensor with QP is still a divariant algebra. So as a ring, as a divariant algebra, it has a unique maximal order. Okay. And this maximal order actually comes from the valuation. So on QP, we have the p-adic valuation. And there is a unique extension of this p-adic valuation onto the whole B tensor QP. And then this extension of the valuation gives you a valuation ring. And that valuation ring is exactly this unique maximal order. Okay. And we will denote this maximal order by OP. And also then as a ring, so the ring OP has a unique has a unique maximal ideal. So everything is very local. Unique maximal ideal, which we will call it P of P. Okay. Then if I quotient I have a ring, and I can take the quotient of its maximal ideal, I will get its residue field. And this residue field is isomorphic to Fp squared. Okay. So moreover, we also know that the element P actually does not generate a prime ideal in O. So P times O actually equals to this maximal order squared. Okay. Another thing is, as we discussed, that B tensor with QP is not isomorphic to the matrix algebra. But if I take B tensor with QP squared, then it is isomorphic to the matrix algebra. Okay. So this means that if K over Q is a quadratic, okay, so quadratic field such that B tensor K is isomorphic to the matrix algebra, then, okay, K is imaginary quadratic. K is an imaginary quadratic field. So it's the if and only if. K is an imaginary quadratic field, and P is either inert or ramified. P does not split, okay? P is inert or ramified in this quadratic extension. Okay, in this quadratic extension. It's an if and only if. Okay. And this K are subfields of B. Okay. So B is a rank 4 Z module, right? B is, or in other words, B is a 4-dimensional Q vector space. So I can try to embed like quadratic fields into B, right? Because it's a divariant algebra. Think about it, right? Like B is a divariant algebra, which means if I take an element in B, then and if I take an element that is not in B that is not rational, then Q join this element will be a field extension, right? And this field extension actually will always be a quadratic field extension, and which will give you a subfield that is inside in B. B itself is non-commutative. But then if I join a single element, I will get a subfield of B. That will be a 2-dimensional Q vector space, a quadratic field. Then, so this quadratic field is, if a quadratic field is contained in B, then B tensor up to this quadratic field extension actually will, you will get the matrix algebra over this quadratic field. And this shows you that this quadratic field has to be either contained in QP square, if I localize, or is contained in the ramified extension of QP. So those are the fields where the quadratic algebra splits. Okay, or the splits means that isomorphic to a matrix algebra. Okay. Okay, so this means, so let me summarize what we discussed so far. We summarize that if I give you an elliptic curve E defined over, let's do a prime field just for simplicity, E is defined over a prime field Fp, then E is ordinary if and Fp bar E, let's actually tensor to Q, why not, is an imaginary quadratic field. So this is isomorphic to K, is an imaginary quadratic field such that P splits in K. Okay, such that Q in K. And then E is supersingular if if its endomorphism algebra is isomorphic to a quaternion algebra such that all the so K imaginary quadratic if K is imaginary quadratic and it is contained in B when if P is inert or ramified in K over Q. Okay. If P is inert or ramified in K over Q. Okay, great. So this is a summary of what we just discussed. Okay. Okay. So this is really background knowledge for what we are going to discuss today. So the main topic of the day is the following. So let E over Q over the rational numbers over Q be an elliptic curve. At all but finitely many primes P, the reduction of E, which we will denoted by E of P, is smooth, is an elliptic curve. Is an elliptic curve defined over Fp. So we want to ask that if I vary this prime, if I vary P, how often, or in other words, at how many prime numbers little p, that how often is EP ordinary? Or in other words, how often is EP supersingular, right? So first of all, we can do an estimate. You can think about an estimate. This estimate comes from another way to determine, to define ordinary versus supersingular. So let AP be the trace of the Frobenius section acting on the L-addictate module of the reduction EP. Okay, then EP is supersingular. Okay, recall that our P is greater than 3. EP is supersingular if and only if AP is 0. Okay, if and only if AP is 0. So we know that from Hasselbalch, we know that AP is bounded, absolute value is bounded by 2 times square root of P. So this means that if AP is randomly distributed, means that if I vary the primes P, the number AP is randomly chosen in the interval between minus 2 square root P to positive 2 square P, then the chance for AP, equals to 0 should roughly be 1 over square root of P, constant times 1 over square root of P, because my interval is of the size of 4 times square root of P, like something like that, right? So then this means if I sum over all P bounded by a constant number X, I should get the supersingular prime should be of the size square root of x over log x, okay? Which is, well, is little o of the number of all prime numbers, right? So this is little o of x, right? It's little o of x over log x. So this is to be a density zero set, okay? So this is a special case. So this is the estimate. And this estimate is a special case of a much more general and wide open conjecture, the long-Chorlton conjecture. Okay. So this is assuming that the APs are randomly falling into the interval of size minus of the interval minus 2 squared p and 2 squared p. But on the other hand, if my elliptic curve depend over a global field, if E has Cm, then the distribution of AP is not random. Okay. So let me state the theorem of Shimura-Taniyama. It says let E over a number field L, so this is number field L, be an elliptic curve with Cm by order in a imaginary quadratic field K. Then let P be a prime of L lying above, or like with characteristic little p in Q lying above a rational prime P. Okay. Lying above P, and also E has a good reduction. That's good reduction at P. Okay. Then the reduction EP is supersingular if and only if the rational prime P is inert or ramified in K. Okay, so let me draw the picture for you. So this is my rational field Q. Okay, this is a field L where the curve E is defined over. So the E is defined here, and here is the imaginary quadratic field K, which is the K is the endomorphism algebra of E. Bar E cancel with Q. Okay, then I have a prime. I take a prime P inside L, and it lies above a rational prime P. Okay, so then the statement is that E mod P is supersingular if and only if so P does not split in this K over Q extension, right? Which, if I use a Legendre symbol, it just means that so let K equals to Q adjoint square root of minus D. It just means that minus dP does not equal to 1, right? And then from quadratic reciprocity, this is the same as a congruence condition. Is this a congruence condition on the prime P? So in this case, congruence condition on P essentially mod D, right? So this mod may be like 4D, worst case scenario 4D, right? Something along the lines. So this tells you that if my elliptic curve has Cm, then I actually, first of all, not only I know the density of primes at which E admits supersingular reduction, I also very explicitly know which primes. Okay, I also explicitly know the set of primes at which my elliptic curve admits a supersingular reduction. Okay, so let me explain why this is the case. Actually, this follows our previous discussion. The discussion of the follows from the discussion of the endomorphism ring for elliptic curve over finite field. So namely, let me just state one thing about the proof. So ideal proof. So essentially, it follows from the fact that there is a fact which is so first of all we're going to extend the field L such that K is containing L. K is containing L. I'm going to extend L so that K is containing L. So this means that all endomorphisms. So we have discussed that all endomorphisms are defined over the field the field L and K, right? Are defined over L. Thus, all endomorphisms are defined over L. So then it follows from the fact that, so this is a deep theorem, which is the endomorphism of E over L actually injects into the endomorphism of EFP under the reduction map. It injects. Okay. So then this means that, well, this means that if, you know, this means that the field K is contained inside FP EP tensor with Q, right? So then this means that depending on whether P splits or is inert in K, the endomorphism algebra of this elliptic curve or finite field contains an imaginary quadratic field with P splits or inert or ramified in there. And this behavior P exactly tells you whether the elliptic curve is ordinary or supersingular or not, right? Okay, so this is the idea of the proof. It relies on the fact that the endomorphism ring of the elliptic curve or global field injects into the endomorphism ring of the reduction. Okay, so this is proof. Okay, so this is the case for CM elliptic curve. So what about a journal elliptic curve? So this question, right? Now we actually know the answer for CM elliptic curve using the Shimura-Taniyama theorem. But what about when E elliptic curve does not have complex multiplication? So first of all, let me state a theorem there. So we can actually restrict to, so Serre says that let E over L be an elliptic curve defined over a number field. Then the set of primes Z is a non-CM elliptic curve. We already see how CM works. Then the set of primes P such that EP is ordinary has density 1. In other words, is at 100% of the primes, the reduction will be ordinary when elliptic curve does not have complex multiplication. So it agrees with the heuristic of Long-Trotter. Okay. We just currently still don't know this way more refined result. Okay. So this is what we know is the set of ordinary primes has density 1. But on the other hand, you see that from Long-Trotter's heuristic, we expect there are infinitely many primes at which the reduction is supersingular. And this is exactly what Elkis showed. And this is the theorem I want to discuss the proof of today. So Elkis. So let E, we're going to state the variant over Q. E over Q be a elliptic curve. Then there are infinitely many many primes P such that the reduction EP is supersingular. Okay. So this proof is very difficult because as Sarah showed, right, the set of supersingular prime is of density 0. It is very difficult to prove a density 0 set of primes to be infinite. Okay, so let's discuss the proof. So discuss the proof. The proof is actually the same as how Euclid proved that there are infinitely many primes, right? So the point is, let's assume there are finitely many, and then construct a new one. So let me first of all say a little bit of the idea. The idea is assume EP is supersingular for finitely many primes. For finitely many P. Then we let S be the set of all let S be the finite set. Be the finite set containing all these P. And also plus where E has primes where E has bad reduction. E has bad reduction. Okay. And then we want to construct a P, right? Well, directly we want to construct there is a P not in this set, such that EP is supersingular. Well, how would you do that? So, well, the idea is to construct such a P. What you want to do is, well, you want to construct a CM curve E naught, okay, such that so let's call the endomorphism ring of E naught, endomorphism algebra of E naught to be an imaginary quadratic field K. So we want E naught to satisfy. So first of all, what we want is we want E naught to reduce mod some prime P to be isomorphic. Sorry, by P I mean really a prime lying above some P to be isomorphic to E mod some P over FP bar geometrically, such that P is inert or ramified in K over Q. So K over Q, K is an imaginary quadratic field extension. There will be a set of primes which are there are infinitely many primes that are inert in K over Q, right? So all we want to show is that E naught reduce one of those primes. So we know that these are the primes by Shimura-Taniyama, where E naught admits supersingular reduction. Then all I want to show is E naught and E reduced by a prime with this characteristic are isomorphic over P bar geometrically, since supersingularity only cares about a geometric isomorphism class. Okay. And then the second thing we need is we want this P to not be in my set S. Okay. And to guarantee that, okay, so this is what we would want to construct, right? We want to use CM curves to construct a supersingular prime for my non-CM curve E. The reason is by Shimura-Taniyama, I know where the supersingular primes are for CM curves. Okay, so in practice, we actually don't construct. We don't construct the E naught. Okay, not constructing E naught. Okay. Instead, we will construct the field K. Okay. We're going to construct an imaginary quadratic field K, which guarantees the existence of an E naught that satisfies this condition, these two conditions. Okay. So I'm going to construct imaginary quadratic field K. This is what I'm going to do to achieve our goal. So now let me actually give you a proof for a slightly simplified version. So this is a proof. What I'm going to prove is the following, is that given E, an elliptic curve defined over Q, whose J invariant, which I will denote by J of E, I will add one assumption to make my proof much easier, but the idea does not change. I will assume that my J of E is less than 1728. Okay, this is not important. This is not an important condition, just makes my proof look slightly easier. Given an elliptic curve E defined over Q, whose J invariant is less than 1728, and a finite set of primes S, any finite set of primes S, we will show the existence, we will find, or let me say that we will find a prime P not in this given finite set. Whatever finite set you give me, I will find a prime P not in this set, and the reduction of E at P is E of P is supersingular. Okay, I'm going to, so given any elliptic curve E over Q, whose J invariant is assumed to be less than 1728, and any finite set of primes S, we will find a prime P not in S such that EP is supersingular. So if I could find such a prime P, this finishes my proof with the assumption that the elliptic curve I started with has the J invariant less than 1728. Again, this is not an important assumption, just makes the proof easier. Okay, so let's start. Step one, I'm going to pick a prime. Okay, pick a rational prime number, which we call D. Okay, satisfies the following conditions. One, D is congruent to 3 mod 4. So I'm going to take a prime that's congruent to 3 mod 4. Two, for each P in the finite set S, or each P such that it divides the numerator of the number J of E minus 1728, or P is a bad prime for capital E. Okay, if P is one of the three, either it is a prime of bad reduction, or if P divides the numerator of J of E minus 1728, or if P is in my given finite set S, I will ask P to split in Q adjoint square root of minus D over Q. Okay. In other words, is for a P that is in one of these three sets, I'm asking minus dP to be 1, which is a so this is a congruence condition. On the products of this finite set of P. Okay. So okay. And then 3, this is the second condition. So first 2 conditions are all congruence conditions. The third condition is I will take my D to be sufficiently large. Later on, I'll explain to you how sufficiently large. Okay. So first of all, note that such a D exists by Dirichlet's theorem. B congruent to A mod B such that the GCD of AB is 1, then there are infinitely many, so infinitely many such P. Okay, so by Dirichlet's theorem, if I give you a congruence condition, P is congruent to A mod B, as long as AB are co-prime, then there are infinitely many such primes in these congruence classes. So this means that properties 1 and 2 are giving you a big congruence condition on D, and there are still infinitely many such P. And then so that I can pick a sufficiently large one. Later on, I'll tell you how sufficiently large. Okay. And another thing I want to note is that D is 3 mod 4 tells us that minus 1D, this is minus 1. Okay, in other words, is minus 1 is not a square mod D. This will be of important use. This is a punchline. Okay, this will be important use in our proof. Okay, so step 1 is to pick a prime capital D. And actually, the imaginary quadratic field, which I was talking about trying to construct, this will be our K. So we're going to argue that if a K is constructed this way, then it guarantees the existence of a CME naught. Okay, as we desire. Okay, so now step 2, consider elliptic curves E1 through En such that all the endomorphism ring of these EIs are isomorphic to the maximal order. OK is the maximal order of K, ring of integers. I will take all of these elliptic curves. Okay, note from the Shimura-Taniyama, any P that is inert or ramified in K over Q is a supersingular prime for all of these EIs. Okay. It doesn't matter which one it is. As long as P is inert or ramified prime, then all of this, any of these EI will reduce P against the supersingularity curve. Okay, I will consider this set of elliptic curves, and I will denote their J invariance. So J invariance to be J1 through Jn. Okay. So the next step is I'm going to define a polynomial which is called P of D. This is a monic polynomial exactly given by X minus subtracting this set of CMJ invariants. Okay. So recall what we have learned from our lecture series. Okay, so all these JIs are algebraic integers, and they are Galois conjugates of each other. So this means that this polynomial I constructed, actually, first of all, it has Z coefficients. And moreover, it is a monic irreducible polynomial. It is a monic irreducible polynomial with Z coefficients. And another thing is that, now if I evaluate it as a J invariant of my given elliptic curve E, okay, so this is, I evaluate this polynomial, I get I from N JE minus JI, right? This is a number, so this is the element actually in Q, right? So if a prime P divides PD of JE, okay, if by divides, I really mean that I look at the numerator, okay, and if the valuation of this rational number is positive at a prime p, then this means the reduction of E at P is isomorphic to the reduction of one of the EIs mod a prime lying above P, okay, over at P dot. Because that means the J invariant, right? The J invariant at prime P vanishes, right? The difference between the J invariance vanishes, which we discussed that has a modular interpretation, has a meaning. It means that these two little curves actually are isomorphic over at P bar. Okay, great. So this is the third step. Okay. So then the fourth step is to show that. Okay, so now let's think about what we want to show. What we want to show is now we want to show that there exists a P that divides PD of JE, so and P is inert. So we want okay. So actually, let's recall what we want to prove. So we want a P such that P divides PD of JE exactly, and minus dP is not 1, does not split, right? This is what we want. So now the question is, how do I know this Legendre symbol condition? Okay, this Legendre symbol condition, that is difficult, right? Okay, well, how to do this? Well, first of all, with quadratic reciprocity tells us that I can, instead of considering minus dP, I can invert it, essentially consider. So quadratic reciprocity tells me that it's enough for me to consider PD, right? Consider the value of PD. And also, Legendre symbol is multiplicative, right? If I want to assert P of D for some P dividing PDJE, well, it might be enough for me to know what PD of JE over D is like, right? So need to know this information. Okay, so how do we do this? That's the next step. That's exactly the next step. Next step is what you will show is take J of E minus 1728, and then PD of JE. This, if I multiply this JE minus 1728, it is congruent to a square mod D. This statement follows from Durin's lifting lemma. So this actually comes from the idea of if I fix, so we have been discussing, okay, so Durin's lifting lemma, let me just say one sentence about it. So the idea is we have been discussing, I have an E defined over a global field, and consider is reduction, right? Like reduction to EP, this is reduction. So the set of EP curves over Q reduced to EP, right? Then Durin's lifting lemma is essentially considering the pre-image of this reduction. Okay, so the other word is if I fix EP, how many pre-images are there? Because if you think about what this equation is saying, is essentially saying that if I fix so what is this product? This is a product I from 1 to n of JE minus JI. So how do I prove this the square? I can just prove that the JIs, which are the CMJ invariants over Q, when I reduce they always go in pairs. There will be two different JIs over Q, but when I reduce D, they will become the same, right? And how to prove this, the idea is I fix the J invariant over FD, mod D. And then I show that the pre-image always goes in pairs. Every J invariant over D, there will be two pre-images when I try to lift it, when I started the pre-image. Okay, so this is only one sentence I want to explain what Durin's lifting lemma is doing. Okay, so you get this statement. So then this means that either D divides JE minus 1728 times PD of JE, or if it does not, then JE minus 1728 times PD of JE D is 1, right? It's a square, right? So either D divides it or it is 1. So recall that for any P divides JE minus 1728, we know that PD okay. So we know that actually minus DP okay. Okay, so we get this. Either one of these two conditions is true. Okay, now, well, remember what we want was get a minus 1, right? I get a 1. Well, but on the other hand, I don't know the sign of this element, right? So there might be a minus 1 hiding there. Maybe this element is negative. So recall our condition. So I had a condition that JE was less than 1728, right? So so next step is to determine the sign of this number. This times PD of JE. So recall, we assumed that JE is less than 1728. I don't know whether you were wondering that we are going to use this condition. This is where we use this condition. So this means that this part is negative. Now, how large is this part? Well, to determine this number, I need to know. So to determine the sign of PD of JE, we need to know the real roots of PD, right? And the real roots are exactly the real CM J invariants, right? Which corresponds to a CMT curve that's defined over the real numbers. What that means is it corresponds to a lattice, or instead of the lattice language, it needs to correspond a real CMJ invariance exactly correspond to the ideal class groups, ideal classes alpha, which equals to its complex conjugation, right? And its complex conjugation is nothing but exactly alpha inverse. Okay. Alpha inverse. So this means that if alpha equals alpha bar is exactly when alpha square equals to 0, equals to OK. This means that alpha is a two torsion in the ideal class group. Okay. But we know that two torsion for the ideal class group of a quadratic extension exactly follows from genus theory. So from Gauss genus theory, we know the size of the two torsion part of the class group for a quadratic extension. It is determined by the number of primes that are ramified in this extension. So we actually have an imaginary quadratic field extension, and its discriminant was minus d, which is 1 mod 4, which means it exactly is ramified at d, right? So the two torsion of the ideal class group is trivial. So then this means that alpha has to be the maximal order. Alpha is the ideal class, which is represented by the maximum order OK itself. Right, is represented by OK itself. So this means this real root, the only real root is the J value of the J of tau, where tau is 1 plus square root of minus D. So then we use the formula we discussed in class. We know that J of tau is roughly of the size Q to the plus 1 plus 744 plus 19688 Q plus dot dot dot, where Q equals to E to the 2 pi I tau. So this means that as D sufficiently large, we know that J of tau is approaching minus infinity. Okay, which means that this PD of JE will be, as long as D is sufficiently large, our JE will be greater than J of tau. So this means that PD of JE will be positive and their product will be negative. Okay, their product will be negative. Okay, great. Now we're almost done. So then this deduces that so this implies that either, again, D divides this product. Or we know that -1 times the absolute value of this product. The absolute value of this product in the Legendre symbol is 1. Okay. So now if I'm in this case, then combined with, I told you that the punchline is -1D was -1, right? Then we know that this absolute value of JE minus 1728 times PD of JE, this absolute value over D, is actually -1. So this means there exists a positive prime P that divides this product, which I've written 17 times now, PD of JE, such that P over D by quadratic reciprocity equals to minus dP equals to -1. Okay. In this case, I get a inert P is an inert prime, which is what suffices. And then in this case, recall that D does not divide JE minus 1728, so which implies that D has to divide PDJ of E. So I get a ramified prime dividing this. Oh, another thing is we also recall that P cannot divide this vector because I assumed that all the P such that PD is -1, such that minus DP is -1 has to all the primes dividing this vector splits in Q drawn square root minus D. So P cannot divide the first vector. P has to divide the second vector if this Legendre symbol happens. So I will either get a ramified prime or inert prime such that PD of JE mod P is 0. Then that's the end of the proof. Okay, this is all I want to talk about. All of the previous 5 lectures built up to this moment. Thanks for listening.